Hey everyone, back in a new awesome video, and today we're going to continue with our series about classical mechanics. Today we will continue with our videos about collisions. This is the second one of 4 of them. We will introduce the concept of relative velocity, and with that concept in our mind, we will be able to find a very important equation using our momentum principle and kinetic energy principle. That way, we will be able to solve systems with elastic collisions really easily. After that, we will explore the world of 2D collisions. So, let's start! Great, let's try and understand the concept of relative velocity. If we have two bodies moving with velocities v1 and v2, there's a lot of motion in this direction in the picture that really blurs out what is happening and doesn't let us see the most important things. We can eliminate all that motion in that direction by taking another reference frame in which the important velocity is the relative velocity. Relative velocity is defined to be v1 minus v2. In that way, we can assimilate this situation the same way in another reference frame, a moving one, in which v1, object 1, starts moving at the relative velocity and object 2 is stationary. And that is a much simpler picture that will allow us to use more effectively our momentum and kinetic energy principles. Now let's try and apply this relative velocity concept. As you may remember from last time, in elastic collisions such as this one we're going to explore, momentum and kinetic energy are conserved. First of all, we will start working with our kinetic energy principle. We have that 1/2 m1 v1 comma squared, the kinetic energy of the first one, plus the kinetic energy of the second object at the initial state equals the kinetic energy of the first object at the final state plus the kinetic energy of the second object at the final state. Now we can make some cancellations over here. We get 1/2 out, and we are going to group the different terms, the m1 terms and the m2 terms, so that we have m1 b1 comma I squared minus b1 comma final, the initial minus the final, equals negative, because we are going to put the final one first, the initial one first, minus the final one. You may recognize this as difference of squares, and that's what we are going to apply. So this is b1 comma I minus b1 final times b1 initial plus b1 final, and on the other side we have similar thing. It'll load a little bit clutter over there. Now that we have this, we're going to apply our momentum principle, and recall it was that the momentum and the initial and the final state is equal. Therefore, p1 plus m2 initial equals m1 p1 final plus m2 p2 final. Now we're going to group once again the masses on each side of the equation. And now that we have this, you may notice that this thing it's right over here, and this thing is right over here. So we can divide this equation by this other equation. We'll call them 1 and 2, and what we're going to do is to divide 1 over 2. And this is going to give us cancels m1 and these two factors, so we have b1 initial plus b1 final. And on the other side, we cancel the minus, the m2 and this factor, so we get b2 initial plus b2 final. And now, what we can do with this equation is to express it in terms of the relative velocities. So we'll get b1 initial minus b2 initial on this side. And we will get minus b1 final minus b2 final on the other side. This is the initial relative velocity, and this is the final relative velocity. And we have found a very important equation. First of all, we know that the magnitude of the relative velocities stays the same in elastic collisions, and furthermore, we know that they change direction. Therefore, if two balls are getting closer like this, they are going to go away with the exact same relative velocity, but with opposite signs. Right, now let's explore 2D collisions. In these collisions, we are going to have, in our frame of reference, to make things a little bit simpler, we're going to have an object that is going to be moving at certain velocity and another object that is going to be stopped. So this collision is going to be 2D because the objects are not going to be aligned with the velocity. As you can see over here, the object will collide around here on this part of the object, and then this one is going to go in that direction with some velocity and at some angle from the x-axis, and this one is going to go in another direction and at a different angle. So we have 4 unknowns: the velocities and the angles. We will start doing our analysis, and the easiest place to start is to do a momentum analysis using our momentum principle in the 2 different directions we have, I hat and j hat. First of all, in the I hat direction, we're going to have an initial momentum equal to mv1, I, the magnitude of that vector, and this is going to be equal to our final momentum in the I hat direction. There's going to be this velocity times the cosine of this angle and this velocity times the cosine of that angle. It got a little bit overcrowded over there, so we'll rewrite it. And now we're going to make our analysis in the j hat direction. Initially, there is no movement in the j hat direction, so momentum is going to equal 0. And on the end, we're going to have this velocity times the sines. Each of the velocities times the sines. So m1 is the sine of theta 1 final, b1 final, plus m2 times the sine of theta 2 final, b2 final. Furthermore, if we know that this is an elastic collision, we are also going to have our kinetic energy principle. However, note that we only have 3 equations, and as we said earlier, we have 4 unknowns: the angles theta 2 final, theta 1 final, and the velocities b1 final, b2 final. To solve for this, we will need to have some more information that we can get from the different places in which these two objects are, at which point do the objects collide, but that will be a much more complicated analysis, and it's not a level of discourse. That is all for today. I hope you understood how relative velocity and different changes in the reference frame can help solve complicated situations and simplify them into simpler problems. Furthermore, I hope you got some sense about how these 2D collisions really work. Any doubts left, you may ask them in the comment section, and I'll try to answer them in the best way I can. Remember to like the video if it was the case, subscribe to the channel, press the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!